So my name is Yao Liu. I'm a new faculty member at Rutgers. I just joined this fall. And today I'm going to talk about our recent work in addressing the challenges in practical immersive computing. Let's see. Okay, so immersive computing is a new kind of a computing paradigm that provides users with immersive experiences, allowing them to, seamlessly explore virtual or physical environments. And in fact, today immersive computing can be delivered through a number of emerging digital technologies, such as, virtual reality, in which we replace the physical world with a remote or virtual world. Or augmented reality, where we overlay the materials on top of the information that we see in the physical world, and mixed reality, in which we not only overlay digital objects to the physical world, but we're also allowed to interact with all these objects. So immersive computing has a lot of use cases in our daily life. They could be useful for, say, entertaining, education, and among others, such as live streaming of live concert, music event. And in addition, it's also used for other kind of more industrial applications, such as in manufacturing and telemedicine, e-commerce, among others. However, practical immersive computing faces quite many challenges. For example, in order to teleport a user from to a remote environment, then that requires a significant amount of data to be transmitted, meaning that we require a high amount of network bandwidth. In addition to support the interactiveness as promised by immersiveness, we also need to have a very low latency, right? So in today's talk, I'm gonna first describe our recent work on addressing the high network bandwidth requirement of one immersive computing application called real-time 360-degree video communication. And then I will, toward the end of the talk, I'll also briefly describe our preliminary measurement work on the power and overheating issues of immersive applications. Right. So I'll start with 360-degree videos. So sometimes people also call it the virtual reality video. It is a form of immersive technology that allows users to freely navigate camera captured scenes in any orientation. It is highly accessible and can be consumed at consumer grade hardware at low costs. So what is 360-degree video like? So this kind of video that captures the information about every direction surrounding the camera. Such a video needs to be captured using specialized cameras with more than one lenses, including professional 360 camera that has, let's say, 24 lenses, or more kind of user-facing consumer-grade cameras with 2 fisheye lenses. And then the captured information is best represented as pixels on a sphere. So we also call it spherical pixels. So with the omnidirectional information that's providing 360-degree videos, we can obtain immersive experience. Okay. For example, 360-degree videos are best consumed through head-mounted display. Right. So, this head-mounted sensors on this head-mounted display will detect our motions in 3 directions, yaw, pitch, and roll. And depending on which way we are looking at the content that's rendered in front of this display may be different. For example, initially we may be looking at the front of this building, and then if we turn around, the sensor will detect that and will render the the back view correspondingly. Okay. Such immersiveness of 360-degree video allows users to more naturally experience real-time events. For example, they could allow us to more naturally have synchronized online learning, teleconferencing with colleagues, as well as other kind of robotic-related applications such as telepresence or human-controlled robotic navigation. Okay. However, the problem is 360-degree video involves a large amount of video in order to for us to place ourselves in a remote scene, and therefore the first thing we need to do is we need to compress these videos, and existing video codecs such as H.264 work only for rectangular videos, and therefore they cannot be used directly to encode spherical videos. And therefore, we need to first project them onto a 2D rectangular plane before encoding, and we call these projections spherical projection. There are many spherical projections exist. Among them, one of the most widely used is called the equirectangular projection. So the way it works is similar to how we represent the word map. So every pixel on the sphere is mapped to this rectangular plane based on its yaw and pitch values. And so in this projected plane, the pitch ranges from -90 degrees to 90 degrees, and the yaw values ranges from -180 degrees to 180 degrees. But even with spherical projection and then video codecs for compression, transmitting 360-degree video still requires very high network bandwidth. There are two main reasons. The first is that 360 videos are best consumed through head-mounted displays, and these displays are more close to the eyes. This makes the users very sensitive to low-quality video or other visual artifacts. So ideally, we want to have high-quality content rendered to the user on the display. In addition, there's actually a significant amount of bandwidth waste associated with 360-degree videos. So for example, if we were to see a view that looks like this, then in fact, only less than 15% of all the pixels on this equirectangular projected frame is used. And the reason is we human beings have limited, we human eyes have limited field of view, and these head-mounted devices also have different field of view. So not all the content that we download will be displayed. As a result, a significant amount of download data is wasted. With this setup, if we want to have the view in high enough quality, say 2K quality, then a kind of full 360 video frame in a much higher, say 8K quality will be needed. And such video may require, say, 100 megabps of bandwidth to transmit, which may not be easily accessible by end users. Okay. So as I said, one use case of 360 video is real-time 360-degree communication. So in today's internet, the de facto technology for real-time communication is WebRTC. Okay, so WebRTC is an open source framework. It can support multi-party real-time communication of video, audio, and other forms of data, and used by many popular services such as Google Meet, that's widely used for teleconferencing, online education, so on, these things these days. However, WebRTC itself does not provide special support for 360-degree videos. That means these videos are simply encoded and transmitted in whatever spherical projection that's supplied by the attached camera, for example, in the equirectangular projection. And as we showed in the previous slide, with this, with the equirectangular projection, maybe only as little as 15% of data used for rendering view, and the rest are wasted. And as a result, significant portion of received video frame is not viewed. This results in very low bandwidth efficiency and low quality of rendered views. So think in this way, if we have only this amount of bandwidth available to the end user, but we end up wasting much of it for transmitting data we're not going to view, we end up getting low quality. But ideally, we would want to devote majority of the bandwidth to data that we actually are going to view, right? So if we have a way to improve the bandwidth efficiency, then we may be able to improve the visual quality of views that are rendered onto the head-mounted displays. So with this, to address this, we proposed a system called SphericRTC. So it is a content adaptive real-time 360 video communication system based on the open source WebRTC framework. So the main contribution of SphericRTC is that it makes per frame content adaptation decisions in an online manner. And with this adaptation, the goal is we want to devote more pixels on the adapted frame to area on the sphere that are more likely to be viewed in an effort to reduce the wasted data. Okay. And now for real-time communication, we also have this low latency challenge. So to this end, we performed expensive frame transformation operations using the GPU via CUDA in SphericRTC. And in our experiments, we show that the visual quality of views that's rendered in SphericRTC is significantly higher compared to the vanilla WebRTC implementation. Okay. So, at a high level, as I said, the most important part of SphericRTC is this per frame adaptation. So what we decided to do in SphericRTC is we choose to use a spherical projection called the offset projection. The idea here is we apply a offset vector to the sphere so that the content on the sphere may appear to be distorted. So for example, here in this figure with the offset applied, the red shaded area on the sphere will appear to be magnified, indicating that we're devoting more pixels to represent the red shaded area. But for the blue shaded area, it will appear to, we end up devoting a smaller number of pixels to this area. Right, so we parameterize the offset using the vector D, and so to decide such how we perform the adaptation, we're going to have to decide which direction do we want to magnify, which direction we want to devote more pixels to. And we also need to decide how much, what's the level of magnification we want to apply to this specific direction. So to decide this, the offset direction, ideally, we want it to be aligned with whichever direction that the user is likely to view. And to address this, we can use say viewport prediction to decide, and the offset magnitude will have to decide that based on the resolution of the camera supplied image, as well as the resolution of resolution that can be supported by the available network bandwidth as decided by WebRTC. So to give you some high-level idea of how this works, so say that we have an original frame in equirectangular projection that's supplied by camera. Then we, if we apply this offset, in the direction kind of toward the gate, then if we apply an offset with a magnitude of 0.5, then this area around the gate will appear to be magnified. And if we increase the magnitude of this offset vector, this gate area will appear to be more and more magnified. Right, so to this end, we designed SphericRTC jointly with the existing WebRTC framework. So in the existing WebRTC framework, it performs real-time bitrate adaptation. So basically, it adapts the target encoding bitrate of the video as well as the target frame resolution based on the current network condition as feedback by the receiver of the video stream. And based on these decisions, we further make decisions regarding the content adaptation, deciding which offset direction to devote more pixels to and what offset magnitude to use. So for example, initially we may be getting the 4K, the original frame, camera captured frame in 4K resolution. If say WebRTC decides that network bandwidth can only support the transmission of frame in the 1080p resolution, we apply the offset with a magnitude of say 0.5, so that the kind of the pixel concentration direction is magnified. And if there's even less available bandwidth, we may further apply more magnification to the pixel concentration direction. Okay, so this slide kind of shows the intuition behind our adaptation. And here, this slide, we're showing the overall workflow of SphericRTC. So the blue shaded areas are the components either we added to the initial WebRTC framework or the component that we kind of modified from the initial WebRTC framework. In particular, here I want to say that so the frame processing component at the video collector side is a very important component where it needs to perform both content adaptation, applying offset to the sphere, devoting more pixels to a specific area, as well as scaling, producing output frames in certain desired resolution. So WebRTC frame processing only performs scaling, but since we needed to perform both, we perform both in a single pass through a tool that we created and open source called Fast Transforms 360. So we call it Fast Transforms 360 is because real-time communication requires fast frame transformation. It has to be fast enough to reach high enough throughput, for example, 30 frames per second. And therefore, we created this tool that performs the frame transformation using CUDA that can achieve much faster transformation speed compared to, say, CPU-based solutions. So we performed experiments on the various settings, and here are some sneak peek of our results. So we found, so in these figures, we're comparing the PSNR between the ground truth view and the view that's actually that is rendered to the end user. And here we're showing the distribution per frame PSNR. So the results show that under different experiment settings, our SphericRTC consistently outperforms the vanilla WebRTC. And for example, the median Viewport PSNR delivered via field. SphericRTC is 2.25 decibel higher compared to vanilla WebRTC when there's no network there's no network constraints. So this is our work in real-time 360 video communication. And besides this work, we actually have also done other work aiming to improve the delivery of 360-degree video in the on-demand kind of video streaming setting. And we also created an open source tool called FMPEG 360 that can be used for services such as edge assisted view rendering, renders the viewport given the user's view orientation, the desired field of view. It can spatially transcode 360 videos to various spherical projections and layouts with a goal to saving either the uploading or downloading bandwidths. So this is kind of implemented within a fork of the open source FMPEG utility, and therefore we can also take advantage of the encoding and the decoding pipeline of FMPEG. Okay, so so I guess toward the end, I'll quickly mention our other kind of preliminary measurement result. So besides the high bandwidth requirements, immersive application also face significant challenges regarding the high amount of computation that's required, as well as the high power consumption and the potential overheating of devices as a result of the high computation. So to this end, we designed a framework for temperature and power consumption measurement and analysis for immersive applications. So here we're showing you what our framework is like. So this figure here shows the platform. The platform includes Android smartphones that we use as the target phone. And we build a lightweight application on this target phone for collecting system statistics. And then to record the thermal temperature of the phones, we use 2 infrared cameras. And we know that with VR and AR, a big component is that the user will interact with the system. In this platform, we used a robot for emulating user behavior while using these VR and AR applications. So I'll just give you a quick overview of what happened, what our results are. So we tested, put these targeted phone Pixel 4 streaming a YouTube video in the highest possible resolution in VR mode for 20 minutes. We found out that that consumed 8% of the battery, and the smartphone surface temperature reaches near 39 degrees Celsius, which is higher than the threshold for warmth feeling. And then the result for AR application is even kind of worse. We've noticed that the AR we played in an augmented reality game called Minecraft Earth for 20 minutes, and that itself used 15% of the battery. And you'll see that the battery, CPU, GPU, and Wi-Fi temperatures all reached a very high value. So this, poses issues of, whether this high temperature may affect the reliability and durability of the hardware, and if they may occur summer safety risks for the users, right? So, so we think that more work with respect to user experiences using these AR and VR applications needed to be done in the future. So, in summary, despite its very promising, the promising applications that it can bring, immersive computing today still faces many practical challenges. So in our work, SphericRTC, we try to address the high bandwidth consumption challenges in an effort to improve bandwidth efficiency and improve the view quality. But there are, besides this, there are a lot of works also needed toward the improving the power efficiency as well as thermal management for the devices of immersive applications. So with that, I finish my talk. Just want to acknowledge the NSF for supporting the work and my students and my collaborators for working together on these works. All right, that's all. Thank you.